Right. Assalamu alaikum wa rahmatullahi wa barakatuh. Salatu wassalam ala Sayyidina Muhammad. Welcome back to Convos on Campus. Today we have the privilege of hosting a legend in the world of automotive engineering. Professor James Turner has a remarkable 35-year journey in the internal combustion engines. From pioneering Wankel rotary engines at Norton Motorcycles to leading powertrain research for over 2 decades at Lotus Engineering. Now at Coast, he's at the forefront of developing carbon-neutral fuels. We are going to talk about the past, present, and the future of engine. Professor Turner, thank you so much for joining us.
No problem.
Okay, so Professor, with your 35-year journey, could you take us back to the beginning? What first sparked your passion for IC technology, especially your early work in the Wankel rotary engines?
Yeah, okay, so that's an interesting one. Obviously, I'm looking back a very long way now. But when I was a student, and even before then, I was really into motorsport. And that period of time with motorsport was really interesting. There was all sorts of new things being done. We had F1 cars with 1,000 horsepower per litre, and we had incredible rally cars and all sorts of things. And there was just such a variety, and it was just really interesting to me, watch it as someone who didn't really know very much, and gradually sort of find out what you were interested in. We were taught obviously engines at university, and there seemed to be a lot of science behind it, and that was good. But there also seemed to be quite a bit of art, and that sort of mixture of the two was really interesting to me. I remember doing a project, basically a written project about engine performance, and I had to dig out various things, and it just sort of sang to me in many ways. It was just really, really interesting. And I knew then that that's what I really wanted to do. I wanted to do engine work.
That was back in the UK, right?
That was back in the UK, yeah.
Okay.
Yeah, and my first job, I tried to get into the car automobile industry, if you like, and didn't manage to. But I view that as being incredibly fortunate, because I wrote to Norton, so motorcycle company, who by coincidence were developing the Wankel for their own product. And so that's how I got my first job. And that was something I knew nothing about. So there was just loads to learn. And all the time you're trying to work out where it fits against the established technology.
Yeah, the Wankel engine is a really quirky one, right?
Yeah.
Because of the ceiling,
Yeah.
right?
Yeah.
I remember taking a course on IC engines, and I remember the professor was talking about how bad it was to maintain a rotary engine.
It's pretty, that's its big challenge, really. It has been that and combustion. So those two things.
Okay.
Yeah.
What was the first engine you actually touched and played around with?
I suppose properly it was one of the Nortons. I didn't work on the bikes very much. A little bit. I did some of the work writing up, because I was only very junior then, writing up the initial performance runs for the motorcycle, the racing bike at that time. That was pretty exciting when you're only a year out of university. But what I essentially worked on was for a project for an outboard engine manufacturer. And I was dealing with trying to improve the sealing of the engine because of its effect on performance and fuel economy. So that was my part. As I say, I was only very junior at that time, so really just following instructions, but learning a lot as I went along.
Okay, so did you study engines as a core in your in your studies in universities, or you just did a general degree in mechanical and then went into engines? Like, what was the path?
So my degree was general mechanical engineering, yeah.
Okay.
And we were taught engines as part of, if I remember correctly, something called thermal power plant. We did also have another module, so that covered internal combustion engines and steam turbines and things like that. But then there was another module as well on gas turbines, and that was really interesting. And I sort of held on to an interest in gas turbines ever since. But that was the two things at university.
What was the most interesting part from an engine that really sparked your interest? Was it the fact that it's converting or rotary motion to power, or was it the fact that it's literally like an explosion? Like, what was the...
Actually, I think I'd stand back slightly from that. I've always been into things that move. And so ultimately, obviously, an engine or propulsion system is there to move something.
Right.
There are challenges with putting engines into anything, from the heat rejection, noise, sound, power transmission, all sorts of things. And it's all balancing all of those different challenges, which gets to be very interesting, particularly against the background of something that has to move. And I think we have to remember, moving things is fundamental to economic growth. Right?
And
So
everything moves, right?
yeah. Well, a lot of things move.
A lot of things
A lot
move.
of things. Many things. Everything has to be moved at some point. So that's something to remember. All the stuff in here has been moved by an internal combustion engine at some point, including all the people, of course. So we have to remember that. So the IC engine was a massive catalyst for the human race to really start to develop economically.
Right. Yeah, I mean, as a mechanical engineer as well, I'm also biased.
Yep.
I also like things that move because,
Yep.
and what you said is actually true. This new age came about because of the engine, right?
Yep.
You have transportation, moving goods, and it is literally like the bloodline of our civilization now, right?
Yeah. So you remember that the car came about because of the internal combustion engine. It wasn't the other way around. The enabling thing was being able to produce enough power to move a carriage under its own automobile manner. Yeah. And we'd had horses before then, but they're really expensive to run, horses, and they're obviously very difficult to keep and control as well. And so it really was a massive catalyst for human development, in my opinion. Other people might disagree, but for me, I would definitely put the internal combustion engine as mankind's number one invention. I actually think, and I guess several people will laugh when I say this, but I actually think the computer has got some way to go before it has such a big effect on human development.
Computers, huh?
Computers, yeah.
Why would you, you're just looking at how things, you're looking at the delta, or?
No, I'm just looking at the way that the amount of value and wealth that's been created as a result of improving people's ability to travel and transport things. Yeah. Economically, you can link the wealth and transport very tightly together. And it was the cost-effective IC engine that enabled us to start transporting things and moving people around much, much more easily than before. And yes, all right, so we do fantastic things with computers. And I would say one of the amazing things we do with computers is control engines nowadays in such a way that's just incredible. But I know we do those. I know we can do all sorts of different things. But in terms of general mankind improvement and standard of living, I don't think anything competes with internal combustion.
Nothing compares. Okay. All right. So your career at Norton, from Norton to Cosworth.
Well, yeah. I had a short period at Lotus, but we'll come back to that.
Yeah. So then 21 years at Lotus. Right?
In total, yeah.
Yeah. So finally in academia, how had this blend of high-octane industry, and deep academic experience influence your approach to research?
Okay. So I think I'm not the most practical of people, but working in the automotive industry, it definitely gives you a feeling for whether something can be productionized or not. So although no one would ever think that I was ever going to be able to rebuild anything really complex, but I know just feeling whether it's feasible to go and try and productionize something. And that is the one thing that I think I brought from one side to the other. The world's full of mad inventors. I'm classed myself as one as well, quite joyously in many respects. But if you don't have that feeling of, or having worked in the industry for a while, is this sensible or not? We used to call it the laugh out loud test. If it doesn't survive the laugh out loud test, then you really shouldn't go near it.
What is that test like?
Well, it's just when you see something, does it make you laugh? Yeah,
Right.
as an idea.
Okay.
If it doesn't make you laugh, then all right, it might be worth looking at. But if it makes you, something, that's not going to work. That sort of thing.
So that's the benchmark.
Yeah. And our biases and feelings and likes and dislikes always come into it, and that influences a lot of things in the auto industry. But there is room for personal opinion as well as all the hard science in engines. Otherwise, they'd all be the same, and that's a pretty wonderful thing, really. Engines are the result of human thought. Yeah.
Brilliant thoughts, actually.
Yeah. Well, yeah, but many different types. You can look at they're completely different, but from two different manufacturers. I know a lot of people would just see them as boxes, but as soon as you're an enthusiast, you pick up the differences just visually.
Well, no, it's what is the most interesting part of an engine for you? For me, it's like the camshaft. The timing of it all is.
That's a really interesting question. I don't really know, because I find it all interesting. I find the whole notion of comparing one type of engine to another and the applications that they're put into is really an interesting thing in its own right. So that's pretty abstract. I suppose what goes on in the combustion chamber is pretty interesting, because that's where obviously that's its reason to be. You spark the charge, it burns, and from that point onwards you're trying to minimize the losses, but you still have to burn it efficiently, and you look and see the stresses that everything's under. So I did some calculations recently for an article I wrote for a motorcycle engine, and at peak power, when you're on the tank doing whatever it is, full load in the combustion chamber, you've got 5 tons acting on the cylinder head, trying to push it off the block, right?
Right.
Just
yeah.
at peak pressure. Okay, and you're over this thing, and it's got to hold together, and you calculate these massive numbers, and I still find it absolutely amazing that they hold together. To be honest, when you look at the numbers on the pages, wow, and the numbers of cycles these things do, and just absolutely incredible.
It's incredible, yeah. It's like the average, I think I remember reading the average lifespan is about 250K, right? For an IC engine.
For a light duty engine, it's much more for a heavy duty
Give or
engine.
take.
Yeah. You'd be pretty pleased if in general usage, all your engines were getting to 250,000 kilometers. Yeah, so sorry, I think in miles, so it's about 150,000 miles, and that's sort of the general sort of life of a light duty engine in a car.
And as a mechanical engineer, like fatigue, all these parts are designed to withstand a large amount of load and fatigue, right? It's
Yep. Yeah, it's all a challenge. So in engines you've got massive temperatures, massive pressures to deal with, and you've got all these parts which require very high tolerances to be machined, and then they've got to be made to be really cheap so people can afford them. That is the real magic of it, and an awful lot of engineering science has been done over the last 150 years in getting to where we are now. In actual fact, 9th of May next year is the 150th anniversary of Otto's first engine.
Otto's?
Yeah. So
when?
The 4-stroke engine.
The
9th of May.
The 9th of May next year?
Next year.
Ah, right.
Just by coincidence.
Okay.
So many people would think, oh, that's a really old piece of equipment. It must be terrible, it's really old. But really, apart from the operating cycle, modern spark ignition engines don't really bear much resemblance to Otto's engine. And that's because of the technologies that have developed with the industry have allowed us to make afford it. And that's been the trick.
The economics of things.
Yeah. So the IC engine has never, ever really had any subsidy. Yes, many people would say, but it's had the subsidy because we haven't cared about the CO2 emissions over the years. But I don't mean that. I mean economic subsidy to make the product affordable. Yeah. So that's an important consideration when you think about what we're trying to do now with decarbonisation. Yeah, so all of that is really important in terms of how it's managed to develop. And a lot of the techniques that were developed for IC engines, a lot of 3D CFD, for instance, basically came out of the auto industry. Certainly a lot of the software was developed for flows inside of engines.
Right.
Yeah.
Okay. I didn't know that.
Yeah. Yeah. As you know, the productionized software.
Mm.
Yeah.
Right. Right. Okay. I mean, it's transforming the world and still is, right?
Yeah. So, yeah, okay. How do we say that? So some numbers then. We currently make about 95 million engines a year in the auto industry. So that's one every 3 seconds. No,
One
sorry,
every-
I got that wrong. It's 3 every 1 second.
3 every 1 second.
3 every 1 second. And basically every single one of those has a buyer, right?
Right.
So very few are sort of stockpiled. Yeah, a few here and there, but essentially there are 3 people every second that are prepared to buy something with an internal combustion engine in it. Yeah, and they do that because it gives them a fantastic cost to utility ratio. It absolutely fits their life. It gives them what they need. So those things is very difficult to challenge.
Yeah, we're going to touch up on
Yeah.
the utility
Yeah.
and the efficiency, and how scientists look at engines in a different way
Yeah.
than engineers. So that work at Norton eventually led you to winning the Isle of Man.
Well, Norton did eventually, yeah. I mean, I was only there for a year.
Okay.
But like everyone starts out at the beginning of any kind of career, the first bit is vertical in terms of learning. So
Okay.
it was a really good year. Yeah.
Have you learned anything special from that experience?
Yeah, I think the interesting thing for me is what it led into. As I said earlier, I briefly, about 2 or 3 years, I went to Lotus before I went to Cosworth. And when I went for my interview with these powertrain engineers who'd been doing that job for about 20 years, all they wanted to talk about was Wankel engines because they knew nothing about them, right? So actually that first year working at Norton was fundamental to me getting a job at Lotus. And that really was the thing that really triggered my career in terms of wanting to understand things and make things better, shall we say.
Okay. How far? So did you get that job as soon as you graduated, or did you have to wait for?
I had to wait for a few months before I got the job at Norton.
Yeah.
Yeah, don't get me wrong, the auto industry is in a real mess now. But back then things were not good in industry in the UK, at least. But that's all I wanted to do. You know, as I said, I as an adolescent, I was really into cars and motor racing. That's all I wanted to do. Yeah.
Yeah. I guess the first impression really matters. I think they left a good impression on you. That was a good, first
Yep.
charge to start your career.
It was fascinating because it was something I'd not been taught anything about. You know, all I could do was try and see what I was dealing with, reading some papers in that area, and then trying to relate it to what I'd just been taught. And it is completely different, the Wankel, to a reciprocating engine. And that in itself was fascinating.
So you started working in the industry on the rotary engine. You never touched, you never worked on the reciprocating engine?
Not for the first year.
Okay.
No.
Right. And when did the transition happen for you to academia? When did you start your master's, PhD?
That was much later. So see, I've only been an academic for how long now? Just over 10 years.
Mm-hmm.
But I'd always, it was the last 10 years at Lotus I led powertrain research, and all these bizarre things. So Lotus, I guess many people wouldn't have heard of them, but anyway, they're pretty famous in the auto world. As successful as Ferrari for a while in Formula One and in lower formulae, and they also made road cars and a bunch of other things that they did. Very much the driving force was their founder, Colin Chapman, and he was really innovative. That was the thing about Lotus. It was very, very innovative.
Mm.
And when he died, which was a while ago, the company had a period of time when it didn't really have much money. And you'll find that when you don't have much money, you really have to start thinking, right? You need to understand how things work because you want to make sure that you're doing the right thing from A to B. You don't want to waste money over much, yeah? But I say the thing at Lotus, fabulous company to work for, really, truly, in my opinion, just the best car company, really. But the shadow of Colin Chapman, the founder, was really long. And there was this overwhelming feeling, I've got to innovate something. Yeah, that was the thing.
How was it like working under him?
He died before I joined. He died about 5-10 years before I joined Lotus.
Okay.
But as I say, the shadow definitely was cast over everybody. And the passion and enthusiasm of the engineers there is definitely related to what the company had done before and what it was still doing when I joined. So it was a great place to be. It wasn't very hierarchical. You might have had a certain grade in the organization, but if you had something sensible to say, everybody would listen to you. And that was a very nurturing environment for young engineers, shall we say. You were taken seriously from quite early on, as long as you didn't say anything stupid.
Right.
Yeah.
Was that culture perpetuated by him, or was it?
I don't know, actually. I mean, there were very few people there who'd worked under him. There was an engineering director had. I think so. I never really thought of that, really. It was just the general feeling of the place. You know? We had come up with some pretty amazing stuff. Unfortunately, the one thing it was never very good at was making any money. So, there was, believe it or not, a period of time, you can go back and look in the history. It was when I was becoming a student that Lotus was Britain's Ferrari.
Britain's Ferrari?
Yeah. No. And you'd find tests of Lotuses against Ferraris, against Porsche 911s. That was the position of the company in the automotive hierarchy, if you like. And obviously now that's not the same. But that's where we all thought we justifiably belonged there. But unfortunately, for one reason or another, lack of investment, we could never make it happen.
Okay. Well, we'll see how it turns out. Hopefully you are one of the pioneers in improving things. Let's flip the coin now. So there's an immense pressure to electrifying everything now. So why shouldn't we simply replace all combustion engines with electric motors?
Okay, so let's think about it different ways. So let's think about the thermodynamic view. Yes, absolutely. Let's do it tomorrow. Can't argue. Much more efficient. Primary energy to end use. You lose absolutely the minimum. Absolutely the way to go. No argument. Done.
Yeah, surprised me there.
Yeah. Okay. Well, that's the thermodynamics. That is the engineering science talking to you, right? Now, the key word in what I just said was engineering, right? A scientist would tell you that we must electrify. It's the best way to use the energy. We shouldn't go any other way, just electrify everything, yeah, because it's the most efficient. An engineer understands things in a different way. Understands that things have to be affordable, they have to be scalable, they have to be desirable, they have to offer people the right combination of cost to utility so that people will buy them, and all of these different things. Yeah, that's what an engineer understands. And against that, absolute efficiency is actually way down the list, really. Can people afford it? Do they want to afford it? Do they want to afford running it? Yeah, that is the thing that gives you a mass market product. That is the way that the internal combustion engine absolutely dominated everything else. Yeah. So when people talk about when it comes to decarbonizing transport, there is no silver bullet. And that's true. And the problem is that what you're going up against is a silver bullet. the internal combustion engine, every single niche that it's moved into has utterly dominated, right? So if you think about a silver bullet is one thing that does everything, yeah, it has utterly dominated. The sad thing, and I know I'm sitting here in Saudi Arabia when I say this, the sad thing is the reason it's been able to do that is the abundance of fossil oil and the cheapness of fossil oil. Yeah. So obviously the concern is the emissions of CO2 from transport. Yeah. But an IC engine doesn't know anything about where the fuel came from, or, you know, is it fossil or anything like that. So it suits a lot of people to have the general public believe that an IC engine has to run on fossil fuels, but it just doesn't. The very first ones, there was no fossil fuel industry. They all ran on biofuel. Yeah, whether it was ethanol in Henry Ford's Model T, or whether it was biodiesel in Diesel's first engine. There wasn't any fossil oil.
You want to talk to her? Can you talk to her? Yeah, go on.
Yeah, so there was no fossil business for fuel. It was, you know, the first filling station was actually arguably created by Carl Benz's wife when she took his car that he created on the first long distance journey, and she had to stop at an apothecary, a chemist's, and get some cleaning fluid, and she put that in the car, and filled up en route with some fuel. Yep. And Benz had sort of realised that this cleaning fluid would burn, and so he could develop an engine for it. And this stuff was just a byproduct of the lamp oil industry, that the lamp oil manufacturers didn't know how to get rid of it. It was just they just didn't want it, and all of a sudden people started buying it, very slowly, but to go into IC engines. And so then you got the two industries start to pick up, yeah, and be symbiotic with each other. But I want to, if anybody takes anything away from this, they should realise that IC engines don't have to run on fossil fuels. We can run them on something else, yeah. And if we can make that cheap enough, and if by the same token, because we could do this, make it miscible with fossil fuel to begin with, we can actually start to decarbonise everything if we can decarbonise the fuel. Yeah. The engine has nothing to do with decarbonisation. It's the fuel that's the problem.
And how does your research, maybe you can give the audience a bit of background, how does your research and what you work on within your group help us get closer in that direction?
So on the engine side, we're always seeking to make engines more efficient. That's been the way for industry for a couple of decades now. Obviously, everybody wanted their engines to be more efficient, so it cost less to run. But then we started to get CO2 emissions regulations, right? And the CO2 emissions are linearly related to the amount of fuel that you burn. Right? So if you make your engines more efficient and you run them on fossil fuels, your CO2 output will fall. Yep. So that's one of the reasons. The other reason, make them more efficient. And if we can get some of this zero net carbon fuel in the future, if the engines are more efficient, then then they will displace more. That fuel will displace more fossil fuel from the fuel pool. Yeah. So efficiency is very, very important, but it's not everything. It's not everything for an engineer. If people can't afford to buy the product, yeah, then you don't make a sale. It doesn't matter how efficient the engine is. If nobody buys it, they'll carry on running something that's less efficient. Yeah, so you have to balance all of these things up together. So I've mentioned efficiency several times, and I've mentioned cost. And the two things are not linked, as I've said. The IC engine is actually very, very inefficient, right? For all sorts of laws of thermodynamics. Right.
Heat and friction
Heat,
and
loss, everything. Yeah. So when you fill your car up, just in general usage, you'll be very, very lucky if about 25% of the energy that you've bought, yeah, actually gets turned into useful work, right, to move the car around. The rest of it all disappears as heat. It all disappears as heat eventually, because when you brake the car, it goes into heat. But it all disappears as heat. But some of it can be used to move the car around, which is what you want. Yeah. And despite that massive inefficiency, it's become massively successful. So don't for one instant think that efficiency is inherently linked to whether something is successful or not.
Right, that's not the metric, right?
It doesn't go together in the marketplace. It's affordability that's the important thing.
Yeah, policymakers, they get to decide, right? What metric to use according to whatever campaign they want to run.
Yep.
What would you say about the value of this deep engineering heritage that a lot of policymakers are trying to bury?
Well, yeah, obviously I've got quite a lot of things to say about that. I suppose they want to cast the internal combustion engine as an evil thing that we've created. And as I said earlier on, no, it's built the modern world. It's as simple as that. Another thing about it is that the whole phraseology about how they approach it, banning the internal combustion engine. Banning, that word. We've banned very, very few things. We've never banned smoking, and yet it's obviously very bad for people. Yeah? And yet they talk about banning the IC engine, the very thing that's done arguably more to drive GDP. The one invention that's done arguably more to drive GDP, certainly from a physical, not a services point of view, but from a physical engineering industry point of view. I would say, if a politician was in here, I would say, show it some respect. It's the fuel that's the problem. It's not the engine.
Right. Because, they're blaming the wrong target, right? It's not, it's interesting.
I know where the wealth comes from here. I'm well aware of that. But it doesn't stop it being true. That's what the fossil, the carbon that's in the ground, digging it out and releasing it as CO2, that is the problem.
Well, this brings us to your current work. You are focusing on methanol and hydrogen. Right? Why does this represent more pragmatic decarbonization path than complete electrifying of the field?
Okay, so of those two, I'll talk about methanol first. Right. So methanol is a fantastic fuel for internal combustion engines of all different sizes, really. The reason I say that is it has one very, very important characteristic, and that is that it is liquid. So it's easy to store on board a vehicle. Yeah. When you burn it, it has a load of really desirable attributes, better than gasoline, essentially, because gasoline is actually quite poor as a fuel compared to a lot of alcohols, for instance, and some of the gases. But it's cheap, and it's good enough. Yeah. So that's the main thing that gasoline has, and it also has more energy per unit volume. Not that that's that important if you actually start to tax or charge for energy rather than volume, but that's another thing. So, basically, yes, it has some disadvantages, methanol. It's quite corrosive, but most fuel systems are tested with it anyway because of that. It is poisonous. It's about as poisonous as gasoline, but nobody goes drinking gasoline, so don't drink methanol. But, it can, perhaps its biggest advantage is you can make it from anything that has carbon in it. Yep. And that includes anything that grows. So some of my research is looking at turning waste product from palm, date palms, into biochemical processes, not a biofuel, but a synthetic fuel by gasifying to get the carbon. So you fix hydrogen to it to make methanol. Yeah. You can make it from anything that contains plastics. You can turn into methanol. So plastics are mostly made from fossil oil, so ultimately that is still a fossil source. Another interesting thing is you can make it from CO2. So if you have waste CO2 streams, which ultimately are going to be emitted to the atmosphere, if you can pluck those out and turn it into methanol and use it in a vehicle for a useful end before you emit it into the atmosphere, that's pretty good. And then the ultimate thing is to, sounds very sci-fi, but it is very possible. Lots of people have shown it. You can extract CO2 from the atmosphere using renewable energy and combine that with hydrogen to make methanol. And if all the stuff is renewable or zero carbon energy, then when you burn that CO2 to release it back into the atmosphere, it's a closed carbon cycle. So it is a no net CO2 emission process.
Mm-hmm. I mean, they always speak about CO2 as a bad thing. Like, is it actually the thing contributing to climate change? And is it actually the thing that, is bad for us?
So I definitely believe that CO2 is driving climate change.
Mm-hmm.
I know some people don't, but you can plot the two things together and they do go together. I know a lot of people will say, well, it's a harmless gas and plants need it and all the rest of it. Yes, but even if we stopped emitting right now, nothing would happen to the plants because the stuff would just keep going around in the enormous CO2 cycle in the earth. So, we don't need any more of it. Let's put it like that. We don't need any more fossil CO2 for the plants or anything because they're on their own closed carbon cycle. Yeah.
Right.
The way to, I suppose, you could say, well, all right, we can bypass the CO2 conversation entirely and just use hydrogen. Okay, so hydrogen is a great fuel when you get it into an engine. The rest of it's really difficult. The transport and the storage of hydrogen and making sure it's safe, that's a massive challenge. So you're now dealing with a gas which will escape if it possibly can. And if it does escape, you have to assume it'll ignite because it's really reactive hydrogen, which is one of the things that makes it really good in an engine, ironically. You can call me a hypocrite, but I choose not to worry about the distribution and storage side of hydrogen because it's a real challenge, which the liquid nature of methanol gets you around entirely.
Mm-hmm. And I guess also the density, right?
Yeah, storage. So the stored energy of hydrogen, yeah. So a couple of things. If you take so methanol contains hydrogen, yeah, and it's obviously a liquid. If I take a litre of methanol, yep, and a litre of liquid hydrogen, there's 40% more hydrogen in the methanol than there is in the hydrogen. And that's because hydrogen's density is so low. Yeah, and that is the challenge. You need an awful lot of it before its energy content per unit mass starts to outstrip the problems of storage, which incidentally is why we use it in rockets. That's because rockets are massive and they store so much energy. And that means it's more sensible to use hydrogen, liquid hydrogen, in a rocket than kerosene or something like that. Yeah, I mean, it's not to say that you can't, but that's the reason why hydrogen is used for rockets.
Okay. What is the latest publication that you did? Like, what is the latest, publication that you, or the latest, interesting finding that you can share with an audience?
Wow, I've got
discovery or something.
Quite a big group, and they're all great, and they all do a variety of things. So it's very difficult to sort of point at one thing. So we do everything from hydrogen combustion through other fuels, through to novel engine concepts, through to we're doing a large project that's funded by Aramco at the moment, looking at heavy-duty hydrogen engines, which is interesting. I suppose the one thing that's really got me interested and quite fired up at the tail end of my career, which is very nice to get to, is I'm looking at this concept called a wave rotor.
Wave rotor?
Wave rotor, yeah. So they've been around for quite a while. You can apply them, they were used for supercharging, but they've been investigated for gas turbines. And in theory, they allow you to convert some of the energy that's ordinarily lost in a gas turbine process. I'm not going to go into the thermodynamics, but it allows you to recover some of what we call the stagnation pressure to a useful end. And we've got some interesting IP at Kaus that we've developed off the back of it. And we think we can make the engines that are in the sort of things that we all fly on, the long distance stuff. We can probably make those slightly more efficient, but also quite a lot cheaper if we can develop this technology in the right direction. That is one of the really interesting things for me at the moment.
What is it called again?
It's called a wave rotor.
A wave rotor.
Pressure exchanger is another phrase.
Okay. And
It's cool.
it's a mechanism, or it's
definitely a machine.
Okay.
So basically, it's got this. Shall we say a typical one might have 30 tubes around the periphery of a drum that rotates, and the drum ends are alternately exposed to high pressure, high temperature gas, and they've got fresh gas in them already. So when the high pressure, high temperature gas hits the end, it compresses the mixture, the fresh gas in the end, and as it rotates, essentially it communicates with a bunch of different ports and gives you a very efficient compression process, right? But it's all done dynamically using shock waves, right?
Okay. And which gas is used?
So for a gas turbine, it's the combustion gas coming out the combustion chamber.
Okay.
And obviously you've got fresh gas coming in the front from the compressor. And what goes out goes to the turbine, which is where the work is extracted. Yeah.
Okay.
But the key thing, I'm going to get really carried away. But the key thing is that the wave rotor operates at the average temperatures that it sees. Okay, so that means that it doesn't melt, right? And it also means that the outlet temperature from the wave rotor can be arranged to be lower than the metal temperature of the turbine. Why is that important? Surely you'd say, oh, we want it to be lower than the metal temperature of the turbine. Well, most gas turbines, certainly the efficient ones in aircraft, they try not to think about this while you're taking off. But the metal in the turbine blades, the feed gas temperature to the turbine is higher than the melting point of the blades, right? We have to force cool with a shroud of fresh air around the turbine blades to stop the hot gas from touching the blade. Okay?
Right.
Otherwise it melts.
The blades of the rotor.
Yeah.
Okay.
Okay. And that's how we get the very, very high efficiencies. So we think all our modeling at the moment suggests that we can move to a point where you basically take out that type of work expansion, and what you deliver to what becomes the first stage, is at a lower temperature than the melting point. And believe me, the technology that is in those blades is staggering. They have to be grown from a single crystal. They have to have passages inside them to carry cooling air that gets blown out the outside and all sorts of stuff. So if you can get rid of that, you can make a useful saving in the cost of the engine.
And that's a leap, That's a big achievement.
Well, every mad inventor thinks he's going to make a huge leap, but hopefully.
You're going below the melting point, right?
Yeah, so the blades get a lot cheaper.
So is this technology it was developed here?
No, it's not. But we have come across something which is not in the literature. So it's not a massive area that's been studied. NASA have studied it, Rolls-Royce have studied it, General Electric, or the turbine, have all studied it in the past. And for one reason or another, they stopped and just followed the normal route of higher and higher efficiency from the normal turbo machinery. The reason they didn't do it was it still takes quite a lot to develop. And the thing that we've stumbled across is probably not too far from the truth. But in all those papers that we've looked at, no one has ever thought of putting more than one stage of wave rotor in. No one. It's not in 350 papers in a relatively small area. And so that's what we're looking at, all the thermodynamics behind it and everything. And in theory, you can certainly, for the small gas turbines, you can really push the efficiency up. The large gas turbines, which are already really, really efficient from a compressor and turbine point of view, they're more difficult because the actual efficiency of compression in the wave rotor winds up being slightly lower than you can get in the turbo machinery. But if you can reduce the temperature of the outlet gas, right, to below the cooling requirements, that changes things quite a bit. The other thing is that the wave rotor, because it operates at this average temperature of the gases across it, you can push the upper cycle temperature up, right? And that is one of the big efficiency drivers on gas turbines. So we think we can get the efficiency back by pushing the combustion temperature up.
Right.
Anyway, that's in the thermodynamics. But the interesting thing is that all links to the machinery and how you think about the whole package. And that for me has always been one of the most interesting things. How does the system work? Not spending my entire career just looking at one thing. How does a system work? If I do this, what effect does it have on the other stuff? And can I trade some of the stuff off to get a better overall result? And that is quite a difficult sell in an academic environment because it doesn't sound very much like fundamental science or engineering, but it is still required. And you need to have some kind of understanding of an awful lot of things to do that. And that's really been my driver throughout my career, just to try and understand these wonderful devices that we have and try and make them better as assemblies.
Right. You mean it's more closer to an engineering effort than...
Yeah, well, yeah, it's definitely engineering. Yeah.
Right.
Many people would say it's not science. Fair enough. But it's still need the engineering science to get there. Yeah.
Right. So now let's take a look at Saudi.
Yeah.
So now at Coast, you're on a unique position. How do you see the advancements in IC technology playing a role in changing the kingdom's energy transition? How do you see things changing or shifting?
So Saudi has some very interesting challenges compared to a lot of other countries in the world. It's very big. So you need to carry quite a lot of energy if you're going to drive quite a long way, because obviously the centres of population are a long way apart from each other. It's very hot. So that gives you another challenge when you think about batteries, because batteries essentially, very, very simple terms, a battery needs to be kept in the same sort of temperature range that you keep a human being in to stop them dying, right? So they're not very high temperature devices, and they don't like cold either. Now, I know we don't get cold here to that extent, but that is the challenge when you engineer a battery electric vehicle. But the thing is, you need to carry quite a lot of energy on board a vehicle. And ideally, if you're doing a long journey, you want to be able to recharge it quickly. And the energy transfer with hydrocarbon fuels is massive. So next time you fill your car up, then when you take the gun out of the pump and you put it in, or somebody else does, when you click the trigger, you have about 10 megawatts flowing through the palm of your hand.
Yeah.
Right? That is the rate that you recharge the vehicle. Now, yes, shall we say, only 25% of that is useful, but that is still 2.5 megawatts. Yeah. The highest battery recharge that we can hope to get at the moment is somewhere around about 750 megawatts, 750 kilowatts.
Kilowatts, yeah.
Some people have claimed they can do 1 megawatt. Right. Okay. Let's think about that for a minute. When you recharge a battery, they're very efficient. They're about 95%. 90 to 95% efficient when you charge them. But the rest of that stuff disappears as heat, right? So if you've got 1 megawatt charger, you have 50 to 100 kilowatts of heat that you have to get rid of while you're recharging the battery. Yeah, and it stresses the battery. But, okay, but you still can't get close to the rate at which you can refuel a liquid-fueled vehicle. Yeah. And that matters. That's part of the utility of the vehicle. If you think about heavy-duty vehicles or in delivery vehicles, they don't. My working definition of a heavy-duty vehicle is: does it make any money when it's stationary? No, they don't. You pay basically for things to be moved, whether you're buying a ticket on an aircraft or whether you want stuff to be moved in a truck.
Right.
You're paying to have it moved. goes back to the transport thing, yeah? And so when they're stationary being charged, they're not making any money at all. And you, at the moment, because autonomy really isn't there, you're paying someone's wages to just sit there while the vehicle's charging, yeah? If he's only charging the vehicle himself by filling the massive diesel tank up in 10 minutes, 5 minutes, that's not much. That doesn't really come down to the bottom line. But if it takes an hour, 2 hours to recharge the vehicle, which then doesn't have much range, you can see why, in terms of utility, we have a real problem with electric vehicles in a commercial sense.
Right. That's, I guess, the most, I would say, inconvenient thing when you're...
It's definitely an inconvenience for most people, yes. And most people, you've then got the problem of the charging infrastructure. So I'm sure it'll get better, but in most countries, most people don't want to interact with the charging infrastructure, which means they want a much bigger battery, yeah, which pushes the price of the vehicle up. So fewer people buy them, and then there's less money to invest in the charging infrastructure. Right, so you go round this, what we call the RIP problem, range, infrastructure, price. It's all linked together. And until you can really push beyond that, and get lots and lots of rapid chargers out there, that's when people will start to think, oh, I don't need to have such a big battery because I know I can always recharge. Yeah? But right now, they don't want to go near the recharging infrastructure. And ironically enough, if you think of that as being the failure point for a lot of light-duty heavy electric vehicles, the real irony in that is really it's the government's job to sort out the charging infrastructure. It's not the vehicle manufacturer's job. The vehicle manufacturers in Europe have all provided what they were told to provide, which was electric vehicles. And now no one's buying them. And that is partly at the root of the terrible problem that the worldwide auto industry is in, that politicians have pushed this on people and it hasn't worked, right? So, politicians who are subject to lobbying, they're advised by scientists, they've gone down this route and they've chosen a winner. And right now, it doesn't look like it is a winner. What do you do? If you take the view from me here that we have to decarbonise, I don't know. It's quite a sad situation, really. I don't know what they do. At Lotus, myself and a colleague, we were advising or suggesting to people that really we should just concentrate on decarbonising the fuel. We started to suggest that 18 years ago now. If we'd actually started doing it 18 years ago, I reckon we'd be in a much better situation now than we are.
Do what exactly?
In terms of CO2 release being stopped, net fossil CO2 release being stopped.
Why would be doing better now than...
Because in 18 years, you would have been able to develop the plants to make e-fuels, as we call them, from renewable energy. And that is, I know many people listening to this will not want to hear, we've got to stop selling fossil fuel. But the reality is here has a fantastic opportunity because there is a repetitive, massive amounts of renewable energy coming from the sun. Yeah. So this is exactly the sort of place that you want to build an e-fuel plant, because if you've got it, if you're trying to link it to wind power, it's really difficult because that's fairly intermittent. At least we know 6 o'clock every morning the sun starts coming up and we get massive solar irradiance through the days, and then 6 o'clock at night it starts to go down again. So then you can work out how you balance all of that. Basically, you can have an e-fuel plant running for half the day. Yeah. Now, they cost an absolute fortune to build. Yeah. But one of the things to realise is once you've built one, you don't have any real cost for raw materials for making the fuel, because it all comes from renewable energy, sun, it comes from water, and it comes from air. Yeah. It's even cheaper than fossil fuel because you don't have to go and dig it. You don't have to pay to pump the stuff out the ground. It's just the air comes along, the water comes out the sea, and the sun chucks the energy down at you.
Okay. And where does the IC engine?
Well, that's a massive important thing in the whole commercial offering, really, because you make the fuel to go in the engines. And there's a massive draw for the stuff. We know that. I did some calculations once. The rate at which we consume fossil oil at the moment, and I'm sure if I went back to it, I could probably persuade myself that it might be wrong, but it's equivalent to 8% of the flow rate of Niagara Falls. Right? That is the rate that we pump fossil oil out of the ground and burn it. So I don't know whether you've ever been or seen Niagara or anything like that.
Yeah.
It's massive. You think 8%, it's just continual oil pouring over the top, just being burnt. That's the rate at which we burn it. And an awful huge amount of it goes into internal combustion engines. You make the fuel what we call drop-in, so it has the same characteristics. It would be miscible with fossil oil. Yeah, then you've got your market. It's already there. Yeah? We just need the right incentivization on, you've got e-fuels being cheaper than fossil fuels. So, yeah, build e-fuel plants here and start to ship it. I've always said this, if Saudi Arabia built an e-fuel plant and started to ship meaningful amounts of it to Europe, there's a fantastic story to be told. You're being told to decarbonize using electric vehicles. Actually, this fuel here contains, when you burn it, there is no net CO2 release because the carbon in it has already been taken from the atmosphere. You don't have to change a thing in the way you go about your life.
Okay. You're in a quite interesting position because you have the pragmatic, looking at the holistic, solution, not just as a scientist, right? Even though you are in the position to be a scientist, right? But you're looking at the cost to benefit still, right?
Yep.
So still the cost to benefit is still up there.
Yeah, absolutely. So yes, just remember that I said they're massively expensive plants to build, but what you make comes from free raw materials. Yeah. So your economic argument is completely different. Yeah. So eventually you keep running the e-fuel plant and you amortize the cost of the plant over long enough and you start making a lot of money out of your e-fuel. Yeah. So that's one thing. So the point about it is when politicians decide that they want to electrify everything, basically they're asking for at least two miracles because they need someone to build the infrastructure and they need someone to make the electric vehicles to use that infrastructure at a price people can afford. If any of that falls down, it just doesn't work.
And you're not escaping the cycle. Eventually you will use fossil fuel to fire up the electrician, like the electrical power stations, right?
No, you wouldn't.
Or just use the
renewable energy or nuclear power.
Or nuclear, okay.
Yeah. So it's got to be fossil CO2 free energy.
Right, yeah. Right. And I guess Saudi is a unique position because it has massive land that is not occupied, right?
Yeah. So actually, I did another calculation. In terms of primary energy, right? So not considering the efficiency of burning it in engines or stuff like that. But if you just look at current efficiencies for solar panels, right? Then at the sort of irradiance that we get here, then the sort of area of Riyadh would generate as much power as Europe uses in its transport fleet. So it's comfortably, by the time you start to include all of those inefficiencies, then around about 2% of the Sahara Desert would service all of Europe.
2%?
Yeah. And the Sahara, is, as we know here, is obviously by no means the only hot desert in the world. So the numbers are quite achievable.
2%, yeah.
It needs investment. The point is that the efficiency isn't very high in all of that processes, which is why scientists that advise politicians just discount it. But the point is, if it can be as cheap and more people embrace the idea, because the cost to utility ratio is exactly the same as they've been used to, then you've got a better solution. Yeah. And the other point is, as I say, if you make them so-called drop-in, then you can have half and half in a tank in the car. Half decarbonised and half not. And then the stuff that comes out the tailpipe, you immediately cut the net CO2 emissions by half. It becomes a scalable solution that can be introduced gradually.
Interesting.
And one thing I would say is, for all that scientists and politicians really don't like the idea, because frankly, I think some of them just want to do away with the IC engine. But for all they don't like the idea, there is no alternative really to decarbonising aircraft other than providing e-kerosene. Yeah, it's the only way, because aircraft need the massive energy density of hydrocarbon fuel to fly, essentially.
And what is e-kerosene?
Kerosene is basically aviation fuel.
I know, but
it sits between gasoline and diesel as you cut the barrel.
Okay. So it's not an eco-friendly.
Yeah. So as you cut the barrel,
I thought you said e-kerosene.
Yes, E for e-fuel. We tend to e-diesel, e-gasoline, e-methanol.
Okay.
Yeah, that's fully decarbonised. That's what we mean by that.
Right. Okay. So what role do you envision the internal combustion engine? Will it coexist with a different powertrain technology? What do you foresee?
Flick to that side. I'm always trying to come up with something that's more efficient, and that's what all powertrain engineers should be seeking to do. Mm-hmm. So one of the ways that we've come up with recently is to hybridize vehicles. So when the engine's working really inefficiently, you use the electric machine. Yeah. And when you have to run the engine, you can use the electric machine, whether it functions as a generator or a motor, you can use that to push the engine into a more efficient area of operation. And then, of course, you can also recover some kinetic energy when you're braking, which we don't at the moment. We just turn it all into heat and push it into the atmosphere. So you can do all of these things with hybridization, and there's a big range of the degrees of hybridization that we can do. Mm-hmm. And that could provide a bridge to full electrification. Now, I'm not down on full electrification. As I said earlier on, it's way more efficient thermodynamically. You can't argue with that. But what it has to be affordable. And it's not affordable at the moment without huge subsidy. So, if it's affordable and comparable to what we have at the moment, absolutely no problem with it at all. Mm-hmm. And that's the automotive engineer in me speaking, because basically it has to be competitive with no subsidy. That's what people are used to.
Right. Do you foresee, or do you see us moving in that direction at all here? Electric
vehicles?
Not electric.
E-fuels?
The renewable energy.
I think the kingdom has an ambition to be carbon neutral by 2060, I think. So somehow, we're going to have to move in those sorts of directions to do that. So we are going to have to bring in renewable energy into the transport fleet somehow, because the transport fleet here is quite a big proportion of the CO2 emissions from the country. Yeah, because there isn't as much engine industry and agriculture are a lot of CO2 emissions from a country.
Okay. All right. What would you say to young engineers who are looking to pursue a career in IC technology today? Is there a room to make a real impact still?
I'm going to say, if you're interested in it, go and do it. You never know where it's going to lead. I mean, I've been spectacularly fortunate, and I'm quite happy to admit that. I found something that fascinated me, drove me passionately, and I've managed to follow that throughout. And every day I learn something new. I try and think of something new as well every day, and that's been great for me. So, if you really do have something that interests you, don't let anybody put you off from it.
Right.
Engines, yes, we're under attack, shall we say, now. But I think the tide is sort of turning, really, in most markets. The shame of all of what's happened from a political point of view is that most of the manufacturers stopped investing in engine technology some time ago. And what that means is, essentially, if we'd kept investing in engine technology, we would be in a better place from an efficiency point of view. Personally, I think at the moment, the planet is in a worse place for all of that, because we haven't been able to sell all the battery electric vehicles or make them to satisfy what the politicians wanted. If only we'd kept developing engines, we'd have been in a better place. And if you look at the CO2 emissions, as measured by, I look at the Mauna Loa CO2 emissions. I plot them every month pretty much. At the moment, I can remember when we went through 400 part per million CO2 in the atmosphere. That was a big moment. And the next big moment was the next year when it was still above 400. That's when it was really taken. We're at 430 something at the moment. And we first went through 10 years ago, 10, 12 years ago. We basically add about 3 parts per million every year. And you look at that data and I'm pretty convinced that it's actually accelerating. It's not turning over.
Slowing down.
So that you can do whatever you want from a policy point of view. Point is, we have this massive computer called the world, which is crunching all the data from CO2 emissions everywhere, and it comes out with one answer, which is the concentration in the atmosphere. You can have all the political talk you like, but I'll tell you this, it's going up, and it seems to be going up faster.
Yeah, a lot of people need to hear this exact point. Like, I guess the main takeaway from this is that the engine is not the one to blame.
Nope.
Right? It's the fuel and how we burn it.
Yep.
Optimize that, and we keep that, we keep that innovation live and pushing.
Yep. But you'll never get to zero net CO2 emissions without taking the carbon out of the fuel. Whether you view that as being just carbon to get hydrogen or ammonia, that's not very likely. Ammonia, from the point of view for land transport, that's not going to happen. But of course, it doesn't contain any carbon. Or you manage to close the carbon cycle in the fuel. So, that's what we're going to have to do eventually, I think.
Okay. What would be one key point that you would give to politicians here who might, watch this? Maybe give them like an insider view, or maybe a pointer or something interesting to look at, or an interesting fact. Maybe you can guide it as as an educated person.
I'd say exactly the same thing as I've said for the last near 2 decades. Invest meaningfully in e-fuels. If you did that here and could show that there was zero net carbon associated with what you can produce, you could have the future.
Okay.
You could own energy supply in the future. If you use the incredible revenues off the sale of fossil fuels to develop the technology to build e-fuel plants, you could supply the entire world forever with a practical fuel.
Right. So you're just continuing on the same legacy.
Yeah. Okay. But it's all hydrocarbons. It's just you can make them renewably.
Nice. Well, it's been incredible to have you, Jamie. Thank you for joining.
Thank you very much.
I would like to ask you, what would you hope your legacy be in the field?
I don't know. If I could wave my magic wand, it would be to pull e-fuels into existence. I've done my bit with that. I really do. I have no guilt associated with running an internal combustion engine of any form on any fuel at the moment, because I know what we were suggesting 2 decades ago would work, and no one was listening at the time. So I am completely guilt-free. I know that as I look back on my very fortunate career working life, I've been really, really fortunate to do what I've really been interested in, engines. But by the same token, alongside, I've looked at decarbonisation of the fuel. The engines are a hobby. Decarbonising fuel is really important. And I've had those 2 elements to it, and they go hand in hand. And I hope that there will be a realisation that that's what we're going to have to do eventually, and we might as well do it now.
Okay. Very well said. Thank you again for your time.
Thank you.
And I hope you guys enjoyed this episode. And thank you for tuning in. Make sure to subscribe to hear more about the people that engineer our future. And thank you very much. Thank you, Jamie.
Thanks. And another thing. And another thing. Just don't get me started.